All right, hi folks. Sorry for the unexpected asynchronous class today. We're going to talk about Chapter 12, which is about extension fields as vector spaces. One of the things that we want to do in this chapter is take some of the things we've been learning about and use that information in a new way. Just cast it in a different light to take some of those beautiful theorems from linear algebra and get them to do some work for us here in modern algebra. So what I'm going to do is I'm going to start with a proposition that's not in our book that reminds us what it means for something to be a vector space. We'll do an example to see what that gets us and do a little bit more review of vector space stuff. Then we'll get some propositions from the chapter and do some examples. So our first proposition, oops, I don't want to do it in light blue. I want to do it in Hamilton brand blue. Okay, proposition 12.G.1 says that if K is an extension field of F, then K is a vector space with scalars from F. And when I say with scalars from F, what you might see in place of that in our book, in other situations, is the word over. It's just faster to write. So a vector space over F, that means that the scalars come from F. And I want to sketch a proof of this. I want to remember what we need to show to verify that something is a vector space. And you may remember it's kind of a long list, but it turns out we've done a lot of this work already in checking that K is, in knowing actually that K is a field. So we need to show that for vector addition, we have closure. If I add two things in K, they stay in K. I need to show that addition is associative, commutative, has an additive identity or a zero, that there's a zero vector in this set, and that additive inverses exist for things in K. And if I look at those things and scratch my head for a minute, I'm saying, all right, I want to show that if I add two things in K, they stay in K. I want to show that addition of things in K is associative, commutative, and has these other properties. It turns out all of that we already know because those are just versions of our axioms A1 through A5 for fields. So K automatically satisfies everything it needs to in order to be a good set with respect to vector addition. And then we've got scalar multiplication. And we're going to hope that it's as nice as this vector addition was. And I'll just remind you that our scalars come from F, which is a subset of K. So these scalars from F are also elements of K, and that's going to help us out. So let's let A and B be elements of F, and U and V be elements of K. So U and V are the things we're thinking of as vectors with some air quotes around them, because they're also just field elements in K. And A and B are these elements in K that happen to live in F that are acting as our scalars. And what we need to show is closure under scalar multiplication. So AU should be an element of K. And it is, because A is in K, U is in K. I mean, I know A is in F, but that means it's also in K. So A is in K, U is in K, and K satisfies M1, closure under multiplication. And you might get the idea that we're going to do a lot of this. Oh, that's a thing that we know about fields. So we also need to check distributivity and associativity and stuff like that. So I need that ABU, sorry, let me say that, A, BU, right, BU in parentheses, should be the same thing as AB times U. That's the associative property of scalar multiplication. A and B belong to F, which means they're elements of K. U belongs to K, and we know that scalar or field multiplication is associative. So this is M2 for fields. We've also got to check two different types of distributivity. We need to know that if I add my scalars and then multiply by my vector, I could have done two different vector products and then added them together. And I also need that if I take my scalar times a sum of vectors, I could have done two scalar products and then added those together. Sorry, up above that's a B. And these two properties are also field properties. They're D1 and D2 for fields. I always forget which one is on the right and which one is on the left. But it turns out since A, B, U, and V are all elements of K, and A and B happen to be in F, that I know I've got distributivity on both sides in K. So this works out. And the last thing I need is that there exists a 1 in F, a scalar multiplication identity such that 1 times U is equal to U for all U in K. And it turns out that it's the multiplicative identity of K, which has to belong to F because F is a subfield. And we're guaranteed that since it's a subfield under the same operations as K, that multiplicative identity is going to be the same in F as it is in K. And so this is because we satisfy M3. So in fact, we got everything that we needed for proving that K is a vector space over F. Again, that over means that the scalars come from F. Just by thinking about what it means to have those field axioms taken a little bit out of context and smushed together or, manipulated a little bit so they end up being the vector space axioms. All right, now I want to do an example. It's a bit of a Mad Libs example because I'm going to leave some information out and we're going to fill it in after the fact. Let's look at the extension field Q adjoin the cube root of 11. Just say let, but I should say consider. I'm not letting it do anything. It is what it is, so I'm considering it. And we can use proposition 10.8 from our textbook to write this down in an explicit form where we know what the elements look like. What proposition 12.1.g that we just wrote down says is that this is a vector space over, again that means with scalars from, Q of dimension blah, which we're going to fill in, because the set B, again, we'll fill that in, is a basis for Q adjoin the cube root of 11 over the field Q. And then we're going to do an indeed and explain why B is a basis. All right, so let's think about what we need to do to figure out what the elements of this extension field look like. We need to know what the minimum polynomial is. And so that'll be the first part of our Mad Libs. Whatever we do, it's going to be because x cubed minus 11 is the minimum polynomial of cube root of 11 over q. And there are a number of ways to see this. The quickest one to write is by Eisenstein's irreducibility criterion with prime p equals 11. Right? 11 doesn't divide the leading coefficient, which is 1. It divides all of the remaining coefficients. The only other coefficient we've got is that 11 or negative 11 if you think about polynomials defined with addition. And 11 squared does not divide 11. So we're in good shape. This thing is irreducible over q for that reason. We could also use proposition 8.12 and say it's a degree 3 polynomial, which means it's irreducible if and only if it has no roots in q. we know the roots of this thing are cube root of 11, which is not rational, cube root of 11 times zeta 3, which is complex with a non-zero imaginary part, so definitely not rational, and cube root of 11 zeta 3 squared, again, has a legitimate complex imaginary non-zero part, so it is not rational, and therefore this is irreducible over Q. So we've got a couple pathways to showing this thing is irreducible. And what that means is that we take A plus B cube root of 11 plus C cube root of 11 squared. We go up to the degree of that polynomial minus 1. Those are our elements where A, B, and C are rational. All right, now the question becomes, how are we going to fill in our dimension box? And I'd like you to think to yourself for a moment, if you had to wager, let's say, your least favorite cat on the guess that you're going to put in for dimension, what do you think it is? So pause the video, ask yourself what you think that dimension should be, come back in a second, and I'll let you know if you've offloaded a cat or not. All right. You still have time to pause if you haven't paused yet. Okay, I'm about to tell the answer, so if you didn't pause, spoiler alert. The dimension here is 3. If you guessed 3, I'm sorry, you're stuck with your least favorite cat. For me, that's the cat Sophie. She's still mine. I guessed 3. It feels like 3 might be the right answer because if we look at how we've written this down, if you remember in linear algebra, I've got like 3 distinct scalars that come from Q. And so if I were going to give this coordinates, I'd have like A times 1, 0, 0, B times 0, 1, 0, C times 0, 0, 1, whatever those basis elements are that gave me those coordinates. And in fact, if I look at the things that are attached to the A and the B and the C, that is my candidate for this. Those are my candidates for the set B. A is multiplied by 1. That's how I get rational stuff. B is multiplied by cube root of 11. That's how I get cube root of 11 stuff. And C is multiplied by cube root of 11 squared. That's how I get cube root of 11 squared stuff. Remember, my scalars come from Q, so I can't do something like cube root of 11 times cube root of 11 to get cube root of 11 squared. I'm only allowed to take these elements and multiply them by elements of Q, the rationals, in order to build things in this vector space. So this is my candidate for a basis, and I want to explain why it is. When we show something as a basis, there are 2 things that we need to do. We need to show that the set spans, so I need to show I can build every element of Q adjoin the cube root of 11 as something that looks like a linear combination of my basis B. And I need to show that this set is linearly independent, that there's no other way to write down, that there's no interesting way to write down 0 with these things. So here's how we're going to do that. Let's do spanning first. The set B spans Q adjoin cube root of 11 by proposition 10.8. So let's unravel what that means. That means that every element of Q adjoin cube root of 11 takes the form A times 1 plus B times cube root of 11 plus C times cube root of 11 squared for some A, B, C, and Q. Which means we've written the elements of Q adjoin cube root of 11 as linear combinations with scalars from the rational numbers of the things in our basis. And that's not too surprising because that's actually how we decided what our candidate set B was going to be. We're like, it kind of looks like A, B, and C are the scalars, and then the stuff, that's there with them, those are going to be our things that we stick in our set B to see if that's actually a basis. So we've got span. If you're, keeping score, we've shown that this thing spans. The next thing that we need to do is show linear independence. What linear independence means is that if you write down a set if you write down a linear combination of these three things and get 0, it must be the case that all of the coefficients that you used, the a and the b and the c, were 0 themselves. And we're going to prove this by way of contradiction. So, by way of contradiction, invoking the contradiction chicken, we're going to assume that the vectors in B are linearly dependent. Assume 1, cube root of 11, cube root of 11 squared are linearly dependent. This means that there exist A, B, C, and Q, not all 0, where 0 looks like A times 1 plus B times cube root of 11 plus C times cube root of 11 squared. Now, in a proof by contradiction, the challenge is to figure out what it is that you're actually contradicting. And in this case, what we might be able to contradict is that the degree of the minimum polynomial is 3, right? We might say, oh, if they're linearly dependent, maybe we can build a polynomial of smaller degree, like degree 2, 1, or 0, for which this element, cube root of 11, is a root. And that would be a contradiction. So that's what we're going to try to do. Now, I just said something about building a polynomial, and so what I want is a polynomial where I can plug in cube root of 11 and get 0, and I want its degree to be smaller than 3. And as I'm sitting here looking at this equation, I see that I've got non-zero coefficients, a, b, and c, and if I think about replacing cube roots of 11 with x's, I'm like, well, that's a polynomial. And I can see from this blue squiggly underlined equation that when I plug in cube root of 11, I'm going to get 0. So let me build that polynomial. Construct f of x equals, I usually do it with the highest term first, so c times x squared plus b times x plus a. And that belongs to q bracket x. I'll just say those are the same a, b, and c as in that blue underline. This polynomial has a really nice property. Has the property that f of cube root of 11, when I plug it in, I get that blue underlined expression, and that means that it's 0. Since the coefficients are not all 0, right, that was our assumption that we had an interesting dependence relation, that we could write down 0 in a cool way with 1 cube root of 11 and cube root of 11 squared. The degree of f is at least 0. It's at least a non-zero constant, because we can't get the 0 polynomial, which has degree negative infinity for us. And it has degree at most 2, and that means that the entire range of possibilities is less than the degree 3, which contradicts that the minimum polynomial for cube root of 11 over q, remember that was our x cubed minus 11, has degree 3. Therefore, b, 1 cube root of 11, cube root of 11 squared, is a linearly independent set. And now we've got that B is linearly independent and a spanning set, which makes it a basis for Q adjoin cube root of 11 over Q. And the dimension is the size of any basis, because one of our lovely, lovely, lovely linear algebra theorems is that once you find a basis, that's the only possible size a basis can take. So what we did was we found the dimension. And I want to make a definition. If V is a vector space over the field F, meaning the scalars come from F, we denote its dimension, which is the size of any basis, if it has one. There's one vector space that doesn't have a basis. The zero vector space has no basis, and it has dimension 0. So that's the only sort of caveat. And we use this bracket colon notation that we've seen before. So we denote the dimension as bracket V colon F bracket. And in our previous example, we have that the dimension of Q adjoin cube root of 11 over Q was 3, right? We had that the basis had 3 elements in it. There were 1 cube root of 11, cube root of 11 squared. And coincidentally, except not actually coincidentally, because we're going to prove that this has to happen, it's the same thing as the degree of the minimum polynomial for cube root of 11. And we have a notation for that too. We call that the degree of the algebraic element, cube root of 11 over q, and we write it as cube root of 11 colon q. So this was a definition from chapter 10. This notation, I mean, sorry. It's the degree of the algebraic element. It just means find its minimum polynomial, yoink that degree, and that is now the degree of your algebraic element. So it's not a coincidence that when we are looking at an algebraic element, the degree and the dimension are the same number. And that's our next proposition. Proposition 12.4 says, if I take a complex number and it's algebraic over the field F, then the dimension, or let's say, then F of R is a vector space over F, the scalars come from F, of dimension n. And using our notation, what that means is that this dimension, which I write using my brackets and colons, which is old school for writing ratios. You kind of think of this as a ratio, the size of one thing relative to the size of another. And we're saying that that's equal to the degree of the algebraic element R, I should say, algebraic over F of degree n. Sorry, left that out. Really what it's saying is that the dimension of this vector space that we built will be the same as the degree of that polynomial. So we can talk about the size, the dimension of that thing. And the proof sketch is exactly what we did for our example. We say, all right, well, let's do proposition 10.8. We know that we can write everything as the span of 1 r squared, blah, 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 up to r to the n minus 1. And then we do a contradiction argument to show linear independence. We say, well, let's suppose that we were dependent. We get this dependence relation. We turn it into a polynomial, and we're like, shoot, this polynomial's degree is too small. So that's how we would prove this thing. This is not a proof technique that you should turn in your writing assignments unless specifically asked to do so. I'll say proof by analogy to the previous example. You can make that argument completely general. So let me do a couple of examples to wrap up our asynchronous class for today. Again, let me apologize for my spotty internet connection that made this necessary. I'm glad I have this in future years. In future years, sorry, you've got to watch this online because I had a bumpy internet connection back in 2021. All right, first of all, the complex numbers, we can think about taking the real numbers and throwing in the complex number I and then making the smallest subfield that contains the real numbers and I. If we do that, we can look at the dimension of the complex numbers over the reals as a vector space because I is an algebraic element. You can think of that as the dimension or the degree of I over R, which is 2 because x squared plus 1 is the minimum polynomial of I over R. To prove that, I'm using proposition 8.12, which says that if my degree is small enough, degree 2 or 3, I can verify irreducibility by making sure that the roots of this polynomial don't belong to R. And I know the roots are plus or minus I. So, sorry, they're not real. Therefore, this is the minimum polynomial. The degree is 2, and the roots, plus or minus I, are not in R, and therefore it's irreducible. It's also monic, and that's how it's the minimum polynomial. The basis for this vector space, if I think about what I need from the sort of proposition 10.8 perspective, I need to get real stuff in there, that's the A, and I need to get the imaginary stuff, that's the BI part. So I use 1 and I as my basis for the complex numbers over R. And this is a way of saying how big is the set of complex numbers relative to the set of real numbers. This is one way of answering that question. I'm going to say it's like size 2 because I need 2 copies of the real numbers, one to go with the real part, one to go with the imaginary part, and that means that C is twice as big, right? How big is this compared to the original field R that I was working in? Let's do another example. To Q adjoin the 4th root of 2. This is over Q. Well, if I think about this thing as a vector space, the 4th root of 2 is algebraic. And so I can look at the degree of its minimum polynomial. The degree of the minimum polynomial, well, we've got to figure out what the minimum polynomial is. I'm going to use Eisenstein's irreducibility criterion here. And my candidate is x to the fourth minus 2. Let me verbally walk through why this is irreducible via Eisenstein's irreducibility criterion. The leading coefficient is 1, so no prime that I pick will divide that. That's great. The prime I want to use is 2 because 2 divides the remaining coefficients, including the constant. And 2 squared does not divide the constant. So that means that this is my minimum polynomial. It's monic, it's irreducible, and its degree is 4. So that tells me that I've got a 4-dimensional vector space when I take the smallest subfield containing the rationals and the 4th root of 2 contained within the complex numbers. Now, notice that in this case we could not have used proposition 8.12 because the degree is 4, which is too big. We can't just check to see that the roots aren't in Q here, because it's possible, even if the roots aren't in Q, that this could factor into 2 irreducible degree 2 polynomials. So this tells me the degree is 4, and if I needed a basis, which eventually I will for things we're going to do later, I can just take those pieces from proposition 10.8 and use those as the basis elements for this space. Eventually, we're going to do stuff with the basis and figure out how to shuffle things around if I want to make a function from one space to another. Let me do one more example, and I will post something that has a few more examples in there. So in the notes posted on Blackboard, you're going to find examples 3 and 4. Here's example 5. I'm going to take Q, and I'm going to put in more than one thing at a time, and we're going to figure out what to do about this. I'm going to take the 5th root of 10 and zeta 3. And I want to say this has dimension something over Q because something else. So let's figure out how we're going to deal with this example. Well, I probably want to do it in a couple of steps. And this is going to lead us to an observation that will help with the next proposition. So first I want to look at Q adjoin the 5th root of 10 over Q. I want the dimension of that vector space. I think this is going to be 5 because I think it's the degree of x to the 5th minus 10. That's irreducible with prime 2 or 5 using Eisenstein's irreducibility criterion. So the degree of that algebraic element, in fact, we're right here, 5th root of 10 over Q is degree 5. So you can check this with Eisenstein's irreducibility criterion and take your prime to be 2 or 5. Either one works. So we've got a basis for that. We've got 1 5th root of 10, up to 5th root of 10 to the 4th is a basis for Q adjoin the 5th root of 10 over Q. I need to then think about how do I mix zeta 3 in here. So now I want to think about the dimension or the degree of zeta 3 over Q adjoin the 5th root of 10. Well, it's going to be the degree of the minimum polynomial of zeta 3. I know that if I were just working over Q, the polynomial that I want is x squared plus x plus 1. We've used this a few times in class before. We know that zeta 3 is a root of x cubed minus 1, but that polynomial is reducible. It reduces into x minus 1 times x squared plus x plus 1. Since zeta 3 is not 1, it's not a root of x minus 1, so it's got to be a root of this thing. And then we use proposition 8.12 to argue that this is irreducible over Q. Well, it turns out it's irreducible over Q because its roots are zeta 3 and zeta 3 squared, both of which have non-zero imaginary parts, and therefore it's going to be irreducible over Q adjoin anything that's real but not complex. So we can use proposition 8.12 here to get that this is irreducible. Its degree is 2, so it's got small enough degree. Its roots are it is plus or minus zeta cubed, but it's really zeta cubed and zeta cubed squared. Just happens that zeta cubed squared is negative zeta cubed, which you can check if you don't believe me. Both have non-zero imaginary components. You can check that using the definition of zeta 3. The imaginary component is going to be sine of 2 pi over 3 times I. 2 pi over 3 is happily not a multiple of pi, where sine is 0, an integer multiple of pi. Non-zero imaginary coefficients, so they're not in Q adjoin the 5th root of 10, and therefore it's irreducible. And this tells me that my basis for Q adjoin 5th root of 10 also adjoin zeta 3 is going to look like 1 and zeta 3. Basis for Q adjoin 5th root of 10 and zeta 3 over q adjoin fifth root of 10. And what happens is we can use this and proposition 10.8 to get a candidate for a basis and then show it actually works out. Right? So if I put all this together in the context of proposition 10.8, I've got q adjoin this stuff. Looks like, well, I've got, oh boy, I'm going to have a lot of coefficients. Let me give them some subscripts here. a1 plus a2 fifth root of 10 plus blah, 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 plus a4 fifth root of 10 to the fourth, plus, and then b1 plus b2 fifth root of 10 plus blah, 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 plus b sub 4 fifth root of 10 to the fourth times zeta 3, where a1, a4, b1 through b4 are in Q. And if I distribute, I think my basis is going to be well, I've got a 1, fifth root of 10, blah, 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 fifth root of 10 to the fourth. And then I've got the same stuff, but multiplied by zeta 3. So then I have zeta 3, fifth root of 10 times zeta 3, blah, 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 fifth root of 10 to the fourth times zeta 3. And I do a proof similar to what I would have done before to prove proposition 12.4 to show that this is, in fact, a basis. We know it's a spanning set because we yoinked it straight from proposition 10.5, which tells us these things span when our coefficients come from Q. And then we do a linear dependence argument. So the way that we wrap this up with a nice bow and call it a proposition is suchly. Suchly a word? I don't know. I'm going to say it's a word. I'll let F be a subfield of K, be a subfield of L, where A equals A1 through AN is a basis for K over F. And we're going to let B be a set B1 through Bm is a basis for L over K. Then, if we want a basis for L over F, basis for L over F is the set where we take the products of these things. We take the A things, multiply them by the B things, all possible pairwise products, and that gives us our basis, which is exactly what we did above. We sort of, I think of it almost as like the area of a rectangle. I've got a basis down one side of a rectangle, a basis across the other side, and I'm like, oh, how do I mix and match these to get all the basis elements? And another way of saying this then is we can say something about the dimensions that tells us that the dimension of L over F is actually the area of that little rectangle, right? We take L over K, that's one basis. Let's say the width of that rectangle that we might draw, times K, the dimension of K over F, which is the length of the rectangle. And we can use this to quickly work out the dimension of some stuff, like, let's say, example 6. If I look at the dimension of Q adjoin the fourth root of 2 and zeta 3 over Q, what proposition 12.5 says is I can do this piecemeal. I can do this as Q adjoin fourth root of 2 zeta 3 over q adjoin 4th root of 2. Oops, adjoin 4th root of 2. And then multiply that by q adjoin zeta 3 over q, the dimension of that. And that's how I will get the dimension. And so here, now I'm like, okay, cool. Well, the zeta 3's minimum polynomial over q adjoin 4th root of 2 has degree 4, so that's a 4. Zeta, oops, I've mixed and matched too far over here. Let me fix this typo. This typo should be 4th root of 2. The way my mnemonic for this is that these should match. Right? My k's should be next to one another in this. And what this tells me is now the 4th root, so sorry, zeta 3, Gibbons, zeta 3's minimum polynomial has degree 2. Right, it's x squared plus x plus 1 still. That's still its minimum polynomial over q adjoin 4th root of 2. And 4th root of 2's minimum polynomial has degree 4. It's x to the 4th minus 2, irreducible by Eisenstein's irreducibility criterion with prime 2, which means very quickly I figured out that this dimension is 8. And if I want to write down a basis, I would write it down exactly the same way that I did before. All right, one last proposition, and I'm going to leave it here, and we will talk about the proof next time we meet. Proposition 12.10 says that if K is finite dimensional, let's say is a finite dimensional vector space over F, and K is an extension field, of F, and if little k is an element of the field K, then a couple things happen. Little k is algebraic over F. So every element in big K is the root of some polynomial with coefficients in F. That's what it means to be algebraic. And the other thing that happens is that the degree of K over F divides the dimension of the big field K over F. And we'll prove this next time, but it's really very nice. It tells us a lot, this gives us a lot of information. It tells us if we can figure out the dimension of the big field over the subfield, then we've narrowed down the possibilities for the degrees of algebraic elements. And if we can figure out the degrees of algebraic elements, we can build up to the dimension of that vector space. So we'll prove this next time. The proof is going to use proposition 12.5. You might imagine that we'd break this up. So taking a proposition 12.5 view of things, we might break this up as K over F adjoin little k, and then F adjoin little k over F. F adjoin little k over F we can replace with the degree of K over F using proposition 12.4. And now we've got that this dimension, well, actually, I think I just proved it, so maybe we won't talk about the proof next time. But this is the key idea in the proof. Since this dimension is equal to that product, what that tells me is that now little k has to have degree that is a factor of the dimension of big K over F. The one thing that we might do is actually show that little k is algebraic, so we still need to show, I lied, I didn't prove the whole thing. I proved part 2. We still need to show that little k is algebraic over F, which means somehow we're going to need to use the fact that big K is finite dimensional to write little k as the root of some polynomial with coefficients from F. And that's kind of a cool proof. So I want to do it together with you so you can ask questions live. And that's where we'll pick up in our next class. All right. Thanks, folks. Sorry for the hiccup in delivery of this lecture. We will talk about this more next time.